Okay, so welcome to the part 8, the last part of this lecture series. So in previous lectures, I was talking about the quantum physics, and quantum physics or theory is already application stage. Then today, as the last topic of quantum physics, I'm going to talk about the recent topics of quantum physics, which is the quantum computers. So recently, for example, in 2019, there was one news from the newspaper Nikkei Online. Then at that time, Google reported supremacy of quantum computing. That is a big news. Then important or interesting point is that triggered by that news, Bitcoin dropped down to under the $7,500. So why this happens? So this is the reason why that the quantum computing is very interesting or attracting. Then anyway, recently you may heard some word, quantum computer, quantum teleportation, or quantum cryptographies. So that also means the quantum computer or quantum application is getting popular in these days. So I'm going to talk about the one topics of this quantum computers. Okay, so today I'm going to talk about the first. Let me review a little bit about the classical computers, not quantum. Then, what the difference between the quantum computers and the classical computers, and the future prospect of this quantum computing. Okay, let me begin with what is the non-quantum computer. So this is recently we see that cell phone, tablet, or PC on the desktop. This is all classical computers. Then these classical computers, so actually we don't care about this detail. However, this is working with 1 and 0 based on the bit. For example, the letter A, that is in the 1-0 binary expression. It's a 01000001A1, and the color of red. Actually, this is a Windows computer. This is 111, 111, and 0. Then if we take a look at the color of this, for example, when you are using the PowerPoint, then try to use a detailed color system. Then the red is, for example, that the 255. 255 stand for is meaning this series of bit 1 and 0. Then in these binary systems, 1 plus 1 is 1, 0. And if we multiply, 1 and 1 is 1, 0. Okay, so then if we take a look at the hardware of these classical computers, the basic circuit is this transistor circuit. Then by combining this transistor circuit, we can construct what is called logic gate. This is the example, not, and, or. This is a table of how that logic gate works. Then in the actual computer, we have a billion of these transistors, then making a so-called CPU, central computing unit. Then actually, when we using the personal computer or computer system, we don't have to care about this detail. So we don't have to care about the computers running with the 1 and 0. However, when we're talking about the quantum computers, it's still a very primitive stage. We need to talk about the 1 and 0 in that level. Okay, so let's move to the so-called quantum bit or qubit. This is a picture that stands for the so-called Schrodinger's cat. So let me try again to introduce this picture. So suppose that cat is inside a room. Then in this room there is a radioactive source. Then if the detector detects the radioactivity from this source, that hammer destroys this glass. Inside that glass is a poison. Then if there is a radioactivity detected by this detector, then cat will die. The point is that before looking inside that room, we do not know cat is dead or alive. Then, according to the theory of quantum physics, we have to express this situation as a superposition of the living cat or dead cat with some weight. Then, only after the observations, we can realize that cat is dead or alive. So we call that this is a quantum state. So we can define the quantum state 1 and 0, then making this phi state. Then after the observation, we can get 1 and 0 with some probabilities. Okay, this is the same slide, but anyway, this is A and 0. After observing this state phi, we can get 0 or 1 with a probability of A square or B square. So this is if we define the bit with a quantum computer or qubit, we call that, that is a big difference between the classical bit. And the classical bit is 1 and 0. And it is always defined throughout the calculations. Whether we observe the bit or not observe the bit, that does not affect the calculation or result of calculations. However, in the quantum bit, during the calculations, inside the computer, it's kept as a state, quantum state phi, that is a superposition of 0 and 1. Then we can see that 0 and 1 only after the observation. Then quantum computer using this quantum bit or qubit, using many qubits, then we can construct the quantum bit. Well, what's the difference between classical and quantum? That's a big question. Anyhow, this is quantum computers. Let's say this is a 3-bit, 1 0, 1 0 1 0 0. We have 3 different bits, and each bit is a superposition in 0 and 1. And if we expand this formula, we see that this is 1, 2, 3, 6 state. Okay, then during the calculation inside quantum computers, this quantum state is kept inside computers. That means during the calculation, there's no way that the state is 1 or 0. Only after the observation, we see that the result is 111 or 000. Then that one observation means the end of calculations. Once, if we observe the state inside the computers, that's the end. We cannot continue the calculation after that. However, that classical computers, you know, that this series of 1 and 0 bit is already defined. And if we take a look at the status of the classical computer, it just gives us the status of the time. Then we can continue that calculations in the classical computers. However, that quantum computer, we cannot continue the calculations. One observation means the end of the calculations. So that is a difference. But anyway, using a quantum gate, it is shown that using quantum gate, it is possible to construct the general purpose quantum computers. Imagine that my explanation so far may be a little bit frustrating. I try to talk about what is a quantum gate, what is a superposition, and what is an observation. However, that it is not explanation of why quantum computer is so interesting, or quantum computer is faster than the classical computers. Honestly speaking, that is not trivial. If we compare the quantum computer and the classical computers, then as I said, the quantum computer can construct a general purpose computers. However, that is important that not all calculations are faster with the quantum computers. The important point is that we need to find the algorithm which is suitable for the quantum computing. Otherwise, quantum computer is not faster than the classical computers. Then, what is a quantum algorithm? Again, this is not trivial. This is just an example. Let's say we prepare the 2-bit, that is 0 and 0. Then apply 1 operations. This first bit is changed to the superposition of the 1 and 0. Then apply another operations to this second bit, going to the 1 and 0. That result in this superposition is this whole state. So the point is that we can get this superposition of the whole state only by 2 operations. If we imagine that classical computer, if we want to prepare this combination of these 4 bits, probably we need the whole operations. So this is a kind of the property of the quantum algorithm. However, it does not explain the quantum computer is faster than the classical computer yet. This is another example of quantum algorithm that is called Grover's algorithm. That is kind of the database search. Let's suppose that we prepare this superposition of this bit. Then we want to try to find this 011 state somehow. Then what Grover find that he find the algorithm that can efficiently find this combination of bit. Apply so-called global algorithm. I'm not going to explain the detail. Once that change the this coefficient a little bit, apply second time, again let's change this coefficient a little bit, and third time you see that coefficient this state is 0.99, the other coefficient is very small numbers. Then you making this state, then if we apply the so-called observations, we can get this answer with the probability of the square of 0.99. This is an example of the global algorithm. What Global did was that he really find the inside the so-called G operations. But still not clear that why quantum algorithm is so clever. This is the reason why that is frustrating. As I said, that quantum physics that was developed in 1920 or 30s. Then this is the name of the quantum algorithm. Deutsch-Josser, Shor, Grover, that was proposed in 1992, 94, 96, only 30 years back. So that means that finding that algorithm was not trivial. After the invention of the quantum physics, that took 70 or 60 years to find the efficient quantum algorithm. Then the reason why that quantum computer is attractive recently is that mainly due to this second algorithm, Shor's algorithm, that is prime factorizations. So I'm talking about why that prime factorization is so important recently. That's related with the cryptography. Okay, let me a little bit talk about the cryptography. That is a picture of the old-fashioned cryptographies. So suppose that this person wants to send a secret message to the person on the right. Then what she did is that put her information inside this box and lock it with a key. Then send it to this person. Then, however, that he needs this key to open this box. So she has to send these keys. Then he can open that box and read the information inside. However, sending this secret key is the most risky point of this cryptography systems. So when she sends this key to this person, if this key is stolen or lost, that cryptography doesn't work. That is a very dangerous, risky point of this cryptography. Then a clever guy invented the so-called public key cryptography that overcome that risk. So in this cryptography, there is two keys. One is a public key, one is a secret key. Then he generated two keys. One is public and one is secret. Then he published this public key to open. Then keep another key in secret. Then when she wants to send a secret message to him, she lock this box with this public key. then send it to him. And for his side, he can open this box with his secret key. With this mechanism, procedures, there's no risk to send the key to one another's. So recently, when we using the website or internet banking is very popular, or for example, if you take a look at your web browsers, then your URL is begin with HTTPS. That means that web browser using this public key cryptography using the communications. So then prime number show up for these systems. Usually, this secret key is generated using a large prime number, let's say P and Q. Then generate this public key with a large N, which is product of P and Q, and this is open to public. Then safety of this public key system rely on the difficulty of factorization of N into P and Q. And usually it is very hard to factorize large number N to P and Q. This is very time confusing, even with the state-of-art classical computers. So the safety of this current cryptography rely on this system, and this cryptography is not only for the banking system. National safety is heavily rely on this cryptography, and if there's a way to factorize this large number to P and Q, someone invented that way to the factorization. That has a very large impact to the entire world, from banking system to the national security. Then this Schrodinger's algorithm with quantum computer show up. This is a prime number of factorization. Then if this algorithm is realized using a quantum computer, that has a very large impact on entire society in the world. That's the reason why that many company, nation putting a large effort on this development of quantum computer recently. But anyway, as I said, not all problem is not good for the quantum computers. This is one example. In the area that quantum computer is good at to solve that problem, that is minimizing energy. Because a quantum computer is a system which consists of many qubit or physical systems. And you may know that physical system tend to go to the ground state of its energies. That means if you can map, you can model your problem to the problem that its solution is the minimum of its energies. That kind of problem or issue is suitable for quantum computers. So that is one area that quantum computer is very good. So this is a kind of the map where the quantum computer is expected to do. Cryptography, decryption, as I said, this is a Schrodinger's algorithm, and also chemical calculations, optimization combination, or machine learning. This area is related to the energy minimization, as talked in the previous slide. Anyway, so far about the 60 algorithms defined as a quantum computer algorithm. However, most of them are just for the demonstrations. One of the issues for this quantum computing is that to invent the algorithm which is really useful and can be applied to these quantum computing systems. Okay, so actually there's another kind of quantum computer which is called quantum annealing. This is using the different physics system with a general purpose quantum computer, but this is specialized for the cost minimization. And because this is specialized for the cost minimizations, it's already developed in the, let's say, the 5,000 bit computers in 2020s. I will talk a little bit later that the general purpose quantum computing using quantum gate, at this moment, we have about a 50 qubit for the general purpose quantum computing. But for this quantum annealing, we already have the 5,000. And this is really, actually this is a real application stage. Okay, let me talk a little bit about the hardware R&D, how we can make the quantum computers. Even the quantum computers, the most basic circuit is that reactance and conductors. Using this electric circuit, we can realize the qubit, quantum bit, with a 1 and 0. However, the difference of the classical computer is that the signal strength is very small. Then, using some kind of electric signal, we can read that information, let's say the bit 1. The point is that, as I said, the signal is very small. Then this is our real operation onto this circuit. However, that noise, thermal noise, can make the similar effect or same effect on this quantum qubit. If we construct a quantum computer with many of these quantum bits, if the only one bit can make an error due to this thermal noise, that could destroy entire computing system. That is a real problem. Then, with the current technologies, to avoid this thermal noise, the entire system cool down. Actually, this superconducting system is used for this quantum computer constructions. Then this is pictures. The most fundamental circuit looks like this, and the correction of this circuit is look like this. It's the order of centimeter scale. Then these chips are embedded into this large machine. Most of them are cooling system to keep with very low temperatures. So this is about the height of the 1 or 2 meters. Then this is the current status. Let me introduce you two famous ones. One is called IBM Q, that is constructed by IBM computer company. That in 2020, that can construct a quantum computer of the 53 bits qubit. The another example is made by Google, that named Sycamore. That was 54 bit in 2019. Then another one developed in China. That was said to have about 70 bit in 2020. So this is a kind of state-of-the-art technology for general purpose quantum computers. But this is not whole stories at this moment. The point is that how long we can keep that quantum state inside that computers. That is about 1 millisecond. That 1 millisecond is not long enough to complete quantum computing. Then we need to keep that quantum state over the time period of the computation, or there's a way to avoid this problem by the error corrections. Error correction means if the 1 qubit or several qubit can make an error state due to the summer noise, for example, there's a way to correct to that error. That is theoretically possible, however, not applied to the real machine yet. This is a situation. According to this situation, the quantum computer I introduced in the previous slide is not a complete general purpose quantum computers. That is called NISQ, NISQ. That stands for Noisy Intermediate Scale Quantum Computing Device. That computer includes that errors, summer noise. However, it still works as quantum computers. So, but not complete quantum computers. Let's say that the Shor's algorithm for the prime factorization. To make this works, we need a quantum computer with a long time of quantum state or quantum error corrections. But it is not realized yet. And current status is that quantum computer is this NISQ system. Even with this NISQ system, some algorithm, chemical calculation, for example, or machine learning, it works with this NISQ system. So probably that it takes some time, I don't know, 10 years or more, maybe 5 years, to develop this general purpose quantum computers, which can be applied to the Shor's algorithm. In the meantime, we can work with the NISQ system or hybrid system, this noisy quantum computer plus classical computers. Actually, at this moment, our real application of the quantum computer is working with this. So this is the station. Okay, so this is a summary slide. Quantum computer is super fast with some algorithm, not always. The example is that quantum factorization, which has a very large impact to the cryptography. And that is the reason why that many persons, many nations working on these quantum computers. And also, however, that's need that needs a real general purpose quantum computer is not realized that. So may take some time to develop the quantum computer which is useful for this factorization. Well, how long it may take? It depends on persons. Well, personally, I'm not so optimistic. It may take 10 years. However, that this kind of field, many people are working. It's possible that a person can make a breakthrough for the R&D of this quantum computing. And if that happens, quantum computer can maybe realized in near futures. Actually, I don't know what will happen in the future, but that field is very attractive, interesting, and many people is working on. So the last message about the final quantum computer is that stay tuned. It could happen. Something could happen in near future. Okay, thank you.